I'm pleased to know that coming all the way here and talking with people who know friends, and we were just chatting over Frisch, and Uriel Frisch is the person who should be quoted for this observation. I mentioned before Cauchy. Cauchy's discovery of 1815, and then a few years later as well. There is a very nice paper, a recent paper, or a series of papers by Uriel Frisch and Barbara Villone, and is about history. It's about history, but it's very beautiful. It's a paper, I don't know, 2014, 14 maybe, something like this. And Uriel Frisch has a wonderful book on turbulence. It's a very compact book on turbulence I would recommend you to have. Is one of the important books of recent years. Well, it's no longer recent. The book is now maybe 20 years, 15 years old. Okay. So we go back to Helmholtz, and in this paper, it's a big paper. He has the conservation laws for vortex dynamics. And again, I, consistently with what I'm doing for the rest of this course, I will focus more on concepts rather than going through these equations. And the concepts sometimes are kind of missing in books, because books report this equation without paying attention maybe to aspects that now we care about, and I will tell you what I mean in a second. So let me state the conservation laws. So this is Helmholtz conservation law. So we have three laws. Let's say that for isotropic flow, vortex motion is governed by this equation, that equation, and also by the following conservation laws. The first is irrotational. Fluid particles. Irrotational meaning curl equals 0 at time t0, remain irrotational for all subsequent times. The second law states that a vortex line is a material line made by the same particles at all times. And the third law is the flux of vorticity, of any portion of a vortex tube is constant in time. Now these vortex laws are presented in basically all books on fluid mechanics and vortex dynamics, but it is, and you can, for example, in Safman's book, you have a very nice proof of these books, of these laws, but it's actually nobody mentioned something that I think is important. First of all, these two laws are about qualitative properties. They do not state anything quantitative. They say that a fluid made by irrotational particles is irrotational and stays irrotational. The particles that are irrotational are going to remain irrotational for any time. And now you think of this. You have a vortex here, and my suggestion is, of course, infinitely long with an axis, maybe here, and your field lines inside. And my suggestion is to think this is a vortex, and you think of the complement of this vortex, okay? So you start thinking, okay, there is a vortex and there is a complement of this vortex. Why I'm emphasizing this? Because I invite you to think to remove the vortex from the fluid, and you would have a fluid with holes, like black holes. So you would have a fluid with complexity, topological complexity, multiply connected domain. So you start to have this view, and if you have this view, these laws are very simple. One says that a region here that is irrotational, stays irrotational at all times, and the region here that is rotational remains irrotational for all times. So is a statement about the same object, if you like. Either I talk about the complement space or I talk about the object itself. I define the object, hence I define the complement space by default. And so I'm saying that this property, the property, say, of vorticity, stays there forever, no matter how I deform it. So it's a topological statement. This is just the two laws are saying that given some vortex tube with a given shape, given geometry, no matter how it deforms, no matter how this geometry, this shape deforms, the region that are hosting the vorticity remain vortical. So it's a topological statement. Indeed, there is no quantitative statement here. Here we have a statement about quantity. It says that the flux which you measure is constant in time. So the third law is very different from the first two laws, and the first two laws, you could condense the first two laws in one law. It's about topological conservation of a certain quantity. Now, okay, you can, in order to prove these things, you have to define a region of vorticity, where vorticity is localized. You can think of a tube, a tubular region, and then you start saying, okay, here the curl is 0, here the curl is different from 0, and you start building your information. So I'm not going to prove these laws. It's not particularly difficult. In Safman's book, a trick is used, a conceptual trick is used, and you think of vorticity omega as a vector, and then you consider each component, and each component, then you start treating each component as a scalar quantity, each component as if it were something, I don't know, like temperature, a scalar. And you want to point out that if a material line, say ink, is colored, instead of ink is one component of vorticity, it stayed colored at all times. Why? You reduce the equations, those one, you reduce the equation on a material line, as we did it already. The Lagrangian derivative becomes the ordinary derivative, and then you appeal to the existence and uniqueness of the theory of existence and uniqueness solution of ordinary differential equations. And so if it stays, if it is colored blue, it stays colored blue for all time. If it is not colored blue, it is not colored blue at all times, etc. So if it is vorticity defined there through these three components, you end up with a set of three ordinary differential equations, and they say that vorticity stays there at all time on the material line, on that material line. So material particle, if they have vorticity, they keep to have it for later times. Similarly is done the first law. This is the second law. The first law is done similarly. You construct a material line where you define that the lack of a certain property and the lack of a certain property by the theory of ordinary differential equation is considered as a solution. It survives at all times. It stays there. The flux of vorticity of any portion of tube is also basically intuitively proven by Stokes' theorem or ante litteram, because Helmholtz didn't use Stokes' theorem. But what I'd like to remark here is the comment that I made. And so, you divide the proof, you take a portion, the flux of vorticity of any portion. So you take a portion, say this portion of a tube, and then on this portion of a tube, you just pay attention to the surface, and you pay attention to the fact that vorticity has a normal component to the surface that is 0 everywhere around this tubular surfaces except here and entering here. And then the volume integral, you reduce the volume integral to the surface integral, because through this boundary there is no vorticity flux. All the flux is here and here. And then you can reduce this if you call this sigma 1 and this sigma 2. Then you have simply that the integral on sigma 1 of omega nu normal to the surface d2 dx is you do the volume integration is given by the sum with a minus side, because it's entering on sigma 2 of omega dot nu d2x. And this is just the integral. When you reduce this to the same and you bring it to the volume, this is just the divergence. This is the curl. Through nu, you apply the divergence theorem, and this is the divergence of omega in d3x, where W is the volume. W is just the volume of vortex tube. Remember, we have no vorticity. There is nothing here when vorticity goes through the surface. We are left with this and this. Then we apply this transform to the volume, and the volume, the integral over the volume is the divergence of vorticity. So this is 0. This is 0 simply because the divergence of vortices is the divergence of the curl of something, which is always 0. Okay, whatever you put here. Well, in particular, U. Okay? So because of this property, this is 0. It means that all this is 0. We have no flux of vorticity through the tubular boundary, only through the surfaces. So we can conclude that if this is 0, then this is equal to that. And if this is equal to that, then flux, no matter how is sigma, is defined that way. Now, clearly, you have here a way to define a flux. So let's call it phi. Then you can use Stokes' theorem, and you identify this flux of vorticity with circulation of U around this tube. C and U like so. Okay. So from there you have also the fact that if you shrink, since phi is constant, you shrink the tube, the intensity increases because the product of the two has to remain constant. All right. Now I mentioned Cauchy, and so Cauchy is behind this because we have also a lemma due to Cauchy. Let's say Cauchy. Maybe I'm wrong to call them solutions, but you will see in a moment why I call them Cauchy solutions. I want to show that for isentropic flow, vorticity is transported. Is transported by the flow according to the following. Omega of rho is dx0, the Jacobian of omega over rho, at time 0. And then I want to add, well, of course, time 0, the 0 indicates the initial position. The equations, these equations are solutions to the vorticity transport equation that we saw there, star. Okay, this is interesting because, again, something that was done in 1815, perhaps, and that wasn't considered interesting, is now quite interesting. When I say it wasn't considered interesting, I mean conserved quantities. It's amazing for us. You know, we pay so much attention to conservation laws, to conserve quantities. You know, if you run into something that is conserved, wow, fantastic. You can, first thing, maybe you think, maybe not myself, but I can implement in a computer and I can control. If you demonstrate that this is conserved, you can use it as a check if your simulation is consistently conserving total mass, energy, momentum, something like that. So it's quite amazing to us now to say that at the time the Academy in Paris didn't pay attention to the fact that he was interested in proving conservation of certain things. And he himself, of course, realized that. So he didn't make a big thing of it. He just, in passing, he said, oh, by the way, this is the case. Here we see something already that, it's interesting. We have, I could stop here and just relax and pay attention to what is written without going to prove anything, just spending time there. We have something, a distribution of a vorticity, a field somewhere, at time equals 0, that is multiplied by this Jacobian, and this Jacobian is, everything is smooth, right? Everything is smooth. It's a combination of derivatives. So there are lots of derivatives there. Everything is smooth. We say analytic. And so of course, everything is continuous. So if I have something here that is in the shape of a knot, then it can be deformed how much we want, but it will be mapped to the same knot type. The knot will change geometry, but the same topology. If there is some topology here, some non-trivial topology here, it will be transported in time by the flow map. And all this emphasis I'm putting is amazing in a sense, because if you just pause and change your mind a little bit, you are saying, well, of course, a fluid motion is about topology. It's the same thing. As long as you allow continuous deformation, this is fluid mechanics, continuous deformation. I can emphasize the same on plastilin, on elastic mechanics, on mechanics of flexible bodies. And I could say, as long as I don't cut the structure, then whatever I do with it, I will deform it, but substantially topology will remain the same. So this is just an amazing observation that probably Cauchy could do at the time, but nobody was interested, so he didn't do it. Or if he did it, he kept it for himself. So I will just manage to show you the second statement. Well, the first statement over there, because I assumed the fact that the Jacobian, the flow map, it has an inverse. Everything is continuous. I can say this. I can say, well, suppose you take an element of a vortex filament or vortex line. You take an element, let me call it delta L, and suppose this is a piece is a material line of a vortex. So is a curl different from 0. Then I can just rewrite this standardly as this arc length, and this is dx over ds by definition of arc length, and this is just I want to go back to the original state. And so I have on dx, and I construct the matrix, the Jacobian matrix. So I have to multiply and divide by these dx, these differentials, at the position time t equals 0. And then when I'm there, I'm done, because you see here is a dx over dx 0. And all this is multiplied by the element, and this is multiplied by the element delta L0. Delta L and delta L0 are just talking to each other through this Jacobian, and this is nothing else than what is written there. It's simply, if you go to the differential, you are happier, you see this, and you think you do the other way around. You think that this differential is an element of a vortex, and then you identify this element of whatever line is with the vortex line. So you can do the same for whatever field you like, because this is just a geometry, if you like. There's no field mechanics in this. So you take whatever, magnetic field, blah, there, and else there. So you have this statement to relate the topology of the initial state to the final state, or better, the final state to the initial state. All right, so we have, of course, here, in this case, as I did before, I should stress that this is my Jacobian matrix. It's not the determinant. Okay, so for the second statement, these equations are solutions to the vorticity transport equations. You have to tell, you have to take a dt of omega over rho, and this is d dt Lagrangianly of, we go back to the original state, so dx 0 times omega 0 over rho. And then we work out the velocity from this, because this is the derivative of x, is the velocity. So we have the transformation of u with respect to the initial position. So this is also a matrix, and this is times omega over rho at the initial stage. All right, so this we can go on. We have du over dx, dx 0 times omega over rho 0. You know where I'm going. And this is du dx times dx d0. The Jacobian times omega over rho 0. So this is rho, basically. Omega over rho du over dx times omega over rho. So we have just to rearrange the last term. Okay, so by rearranging the last term, we have d dt of omega over rho is equal to du dx Jacobian omega over rho, and this is omega over rho times the grad of u. Okay, so Cauchy solutions satisfy, Cauchy equations satisfy the equation of transport of vorticity. We say briefly, very briefly, that whatever is omega and not a link, etc., is in the same topological class of omega 0. So if this is a knot, this is the same knot. If this is a link, this is the same link. There's nothing that can change the topology during evolution. When I say there is nothing, you know, I'm thinking, I'm neglecting viscosity, I'm neglecting all these effects that are very important. So you start thinking of one other thing. You start thinking that topology is conserved is a world where there is no time, so to speak. the time, the dynamical time of the evolution, yes, is there. But if you think of time in terms of entropy, change of topology, etc., which of course is crucial, then is a strange situation here. There is an evolution preserving topology. As soon as you put in dissipative effects, you have real time. So you can decouple the two things. Now, why you want to decouple the two things? Well, you want to decouple the two things. Well, one simple example, one simple reason. Well, if you hit by a tornado, it's so intense that as long as it's alive, makes trouble to everybody. So, in a sense, compared to other forces of nature, you consider this evolution as if it was frozen in a fluid. In other words, if it were, you consider this evolution as if dissipative effects that would calm down this tornado would not be present. One other way to think about this is that topology matters as long as there is some energy localized, and this energy prevails on other energies. So as long as this is the case, you may think that topology tells you a lot. Now, there are situations more abstract where you can like to have topology conserved. Well, there is one case. I can think of my wife, and when I ask her to write something, I'm in trouble, big trouble. I cannot read her writings. You know, you say, well, Renzo, what is talking about? I'm talking about the old times when you went to a bank. I guess nobody goes into a bank now. I never went to a bank. It is now several years with internet, etc., etc. I come to internet, etc., nobody goes to a bank anymore. But suppose you go to a bank and you ask to sign something, and you ask, and I sign this. I signed this, and they're happy. They're happy. But if I do this, they are not happy. Suppose I am the same person. Why they are not happy? Because they cannot recognize my name. You have to recognize something. When you go from here to here, you are allowed to do this. We are always doing this. We are not signing exactly the same thing. We are not stamping down something. But when we are doing from this to this, there is a moment, there is a kind of transition that you cannot go over. Because if you go over, the people say, well, I do not recognize what you are writing. What I'm saying is that if I want to communicate something to you, I have to transmit some information. And this information can be transmitted only if I conserve, during my message, some elements that are considered to be important. And these important elements is, you can call it signature information. The signature information is preserved, is a conserved quantity. I can deform it as much as I want it up to a point. Because at a certain point there is a transition where this information gets eroded or gets changed, dissipated, manipulated, so that I cannot recognize it anymore. But this sounds familiar to the young guys. Is communication technology. We have to send an information that, of course, can be encoded and decoded, but we want to have a signal, an information that is preserving a quantity. And up to now, we've talked about that. Conservation laws, all the time, all the time. Cauchy was not important at the time. Probably if you needed money, they were looking at your face, they were recognizing you, and they were giving you the money. But now is important, because they don't know the faces. And if you need money, you have to encode some information so that that is recognized. No? So I just bought a I gave, it is free of charge, but I gave a debit card to my son recently, free of charge, so it's not a big effort. Then he complained there was no money on the card. This is a different story. And everything was done through face recognition. Everything. Online face recognition. And then they even asked me to redo the take because the face was not properly identified, probably by some computer, with the face I had on an identity card. Because they took a snapshot of the identity card, then the face recognition from my home, and then a bank who knows where, maybe in China or in a remote island in the Pacific, then they decided that I was allowed to have this debit card. Whatever happened was through an exchange of information, and what is crucial here is that is a topological conservation law. It doesn't matter the geometry, but some key features must be conserved, whatever is the manipulation. Of course, this is very, very important for data analysis and for cryptography. That's why it was so important a few years back, maybe still now, information on, there was a lot of work on solitons and integrable system. Integrable system are infinitely many conservation laws associated with integrability, and if you manage to send a signal on a so-called integrable system, then there is no noise that dissipates the information. And if there is some noise, it's so little compared to the conservation laws that are used in that system, an integrable system, that the second-order second-order approximation. So here we are talking about this signature-preserving transformations. Now, the last bit of today, I will end up maybe, I decide I keep, it's better not to mix too many topics. I already do when I talk. So it's about helicity. I want to end up today with the conservation of kinetic helicity. So I have to introduce helicity. And I said, remember what I said at the beginning, I said that this is just a rather recent discovery, because kinetic helicity and magnetic helicity that we see tomorrow have been found to be conserved in the 50s, in the 60s, 58 and 61. So let's say in the 60s. And from the 60s, then many, many other things came, and more specifically the topological interpretation of helicity that came from Keith Moffat's work in Cambridge. Actually, he wasn't in Cambridge at the time. Once we were talking, and he mentioned, I don't know how, if it is, it's already many, many years ago. I was his student, and so maybe I'm misquoting what he told me. But because I was Italian, he said, well, Renzo, actually, the idea of helicity came when we were visiting Italy. And I visited Sicily in Palermo, and then we spent some time as a young people in the hills near Torino, near Turin, and is between Sicily and Turin that came this idea of maybe he was kind to me, so he just said that. He invented the story just to please me. I don't know. So helicity. Helicity. So kinetic helicity was the conservation of kinetic helicity. There are two people, and they tend to mix up the two people. One worked on kinetic helicity and the other on magnetic helicity. One is Voltier, 1958, and the other is Moreau, 1961. One on vortex, the other on magnetic. I will talk about helicity, so I have to define helicity first. Helicity. So kinetic helicity. Is defined by this quantity h. I will take it as a function of time for the moment, integral on a particular region W that now you recognize being the region of vorticity, because I used these symbols to distinguish the regions of vorticity from regions of irrotational fluid, and this is D3x, and so I will put a star just to remind us that this x is a point in W, and this W is, for simplicity, think of a vortex tube, an infinitely long vortex tubes where these lines just denote vector lines of vorticity. So remember, first thing is remember that the integral is on the vorticity domain, because U is associated with vorticity because of Biot-Savart law, but this domain is not outside, it's inside the tube. Okay, so this is the definition of helicity, and we want to prove conservation of helicity, conservation theorem, conservation of helicity. There is a review paper by Keith Moffat on this, 2014, Proceedings of National Academy of Sciences of USA, where he, I think is in that paper, I'm not so sure, but anyway, he's referring to somebody I met personally many times when I was pretty young. My mother is from Geneva, and so I visited Geneva in Switzerland many times. And at a certain point when I was already in Cambridge, but pretty young, 25, I knew somebody in Geneva who was retired there, and his name is Robert Betchoff. And Betchoff is famous for certain equations that are dealing with solitons and their relationship with the nonlinear Schrödinger equation. This is a different story. But because of his interest with solitons, I was interested in solitons, so I met him. And I remember Keith asking me, how did you find him? Well, at the time it was even easier than now. You went to a phone book and you check Betchoff. Betchoff is an easy name to find in Switzerland or in Geneva. So he was the only Betchoff in Geneva. I called and he was him. He spent his life in United States, actually. And Betchoff was very, very interested in this helicity. And he had troubles with the memory because he underwent an operation, etc., etc. But he was telling me that this idea was already in one of his papers, 1961. So you see, very close to these years. And even more interesting is the fact that Keith Moffat's work was 1969. It came later, of course, than these findings. So Betchoff was very much interested because he was interested in turbulence and the role of three-dimensionality in turbulence. And we will see here how is important the role of three-dimensionality in fluids and, of course, the topological interpretation that Keith Moffat gave to helicity. So the statement is very simple, is dH dt equals 0, so that h is actually a constant of motion. All right, so dH, so let's say proof. I will prove to you the conservation of magnetic helicity as well, and I'm sure I find amazing that the difficulty due to the Faraday law for vorticity is reverted here. The proof for kinetic helicity is quite simple, straightforward. But for magnetic fields and for magnetic helicity is a little bit more convoluted. So we will see it tomorrow. Anyway, so we go like this. dH dt is just d dt of the definition over W U omega d3x. And then this is a material volume made of particles that remain rotational at all times. So we get inside d dt and u dot omega. Sorry, I should have put this star. Maybe I'm now forgetting it. Anyway, so we have integral on this W du dt times omega plus u dot d omega dt in d3x star. And then we apply Euler's equation, du dt. We have Euler's equation, and then we need d omega dt that I'm afraid I inadvertently erased. So we have integral minus 1 over rho grad p times omega. I forgot to say something important about the definition of helicity, but I will say it in a moment. It should be there, though. So apologies for this. I forgot to say something about the domain of definition of vorticity. I'll come back to that when it's time. Plus u dot omega dot grad u, and this is on d3x star. I use the Euler's equation here and the vorticity transport equation there. And now, since the div omega is equal to 0 always, because it's a divergence of a curl, then we have dH dt integral on W omega dot grad. I put undergrad whatever I can minus p over rho, and then plus half u squared. When I take the grad, I have u in d3x. Okay? And this is integral W of grad of something, omega, come out, minus p over rho, plus half u squared d3x star. Now, I use divergence theorem. And I have dH dt equal integral. I go to the boundary of W, p rho minus half u squared. Okay. All this divergence theorem, I consider the flux through the surface. So I have a flux of omega through nu being the normal to the surface, d2x. And then, to conclude, I need something that I omitted to say in my definition of vorticity. The definition is that this domain of vorticity or the vorticity beta, is such that the boundary of this domain is always a vortex material surface. So omega such that omega dot nu on the boundary is always 0. Okay? So if we have no flux of vorticity through this bounding surface, then evidently this is 0. So this is rather straightforward. I don't need much algebra. I just need the basic equations and to just insert the basic equations into that. Nothing that I did here reproduces exactly the derivations that Euler, Lagrange, or Helmholtz or Cauchy did. Is the modern version, but this is exactly what it is amounted. Tomorrow we will see the proof of the conservation of magnetic helicity. As I said, it's a little bit more elaborated. You need some identity from vector algebra. The relationship between the two is that u and omega, this is a function, this is the curl of this function. So any field, let me move a little bit farther away from vorticity. Any field times the curl of the field, if this integral admits a topological interpretation, then the same is true for whatever field and the curl of the field defined on the domain of the curl. So the way I said it is exactly the way that Whitehead in 1947, you understood right, said that this quantity, but he didn't refer to vorticity, velocity, nothing. He didn't use Euler equation as we did here, or Helmholtz equation, nothing. He said that a field times the curl of the field, the integral of that is an isotopy invariant. 1947. Meaning that is a topologically conserved quantity. Maybe you have to prove it through, in fluid mechanics, through fluid mechanics tools, but the statement was already around there. Quite interesting. All right. So, yes?
So this conservation law is totally has nothing to do with the Helmholtz theorem.
No, it has to do with we use the Helmholtz theorem here. This part. The omega dt is related to this. So that is what I didn't prove. Helmholtz theorem, transport of vorticity.
So this theorem is also holds for compressible fluid.
Yes. Same can be said for magnetic helicity. Tomorrow we will see it more explicitly, although in a more elaborate way, the role of Faraday's law. Because again, magnetic helicity, I can anticipate, you follow very well, is the integral of A dot B. A dot B. B interpreted as the curl of A. So a field times its curl. And again, there you need to do more or less the strategy is the same. At a certain point, it becomes a little bit more convoluted, but you need the time the transport of the magnetic field, and that is Faraday's, and eventually the transport of the vector potential. So you have to go back to the vector potential, and that is when you need more algebra. Time derivative of the vector potential. But substantially is the same. And so I will duel on this analogy tomorrow. One is, as I as is called, is a perfect analogy. The other one is non-perfect analogy. When I appeal to one of these two analogies, and I refer to vorticity analogous to magnetic field, is actually the non-perfect analogy. But you can do the same with another helicity. I want to talk about, there are a number of helicities because a field times its curl. For example, magnetic field times the curl of magnetic field, which you know is one of the Maxwell's equation, is current. Okay? I can just mention these two things. One is magnetic helicity. I will talk about this tomorrow. Say H M, and this is the integral of A dot B B3 EX star on, let me say W, just to be clear, on the points of B. But there is also some other helicity. I don't know the name. You know the name? I can't remember the name for this one. But anyway, J dot B, where J is just the curl of B. This is electric current, and that is magnetic field. Sorry to the strong physicist here, because I'm putting all the constants equal to 1. Of course, here you know there is a mu, a permeability somewhere, 1 over.
What's the difference between the X star and the X?
Say it again. Between?
X star and the X. The difference.
I said it is about this. Any point inside the tube, this is an X star. Any point outside the tube is an X. So the integration regards the domain of definition of vorticity, of magnetic field, and in this case, this is the current, so the current. So if you have currents flowing in fluid and they form knots or links, then you can attribute topological meaning to these type of configurations. Because helicity would be conserved, and I cannot anticipate too many things, but last lecture would be totally devoted to interpretation of helicity in terms of topology, of linking numbers in particular. Yes?
Is helicity a useful concept for viscous flow? Of course.
I have... yes, it is useful. Can you tell me why? You posed the question to me, I know. But I know the answer, and I want to know if we have a sense together, I mean, of...
Because we can always define...
Okay, let's suppose I don't know the... I don't know. Let's do it as an exercise, okay? So it's a conserved quantity, right? It's a conserved quantity. But I know your point. You're saying, well, viscous fluids. Okay, so we have other conserved quantities, right? So, for example, I don't know, energy. Is energy conserved in a viscous fluid? No. How much it is dissipated? Then we can say something. We measure dissipation of energy. And we may say that energy is important for some reason, right? Because it gets transferred, because it serves a purpose, power, whatever. Essentially because it gets transferred. It is dissipated, but it gets transported, it gets transferred. It gets transferred a part of it. So it's important because we recognize, although we don't measure, we don't know, but we intuitively think that, if I throw a boulder, a mass on something, then this will react. If we throw it in the water, there will be dissipation. But, the amount of momentum I give is transferred. So we have the idea that energy in that sense is relevant, is going to be dissipated, but a great amount survives in the impulse effect. Okay, more or less is the same reasoning here. Helicity is conserved in ideal fluids. How much it gets dissipated? This is the question. Because if it is eroded instantly, well, there's not so much interest. But if it gets eroded a little bit, maybe like energy, that would be great. That would be important. And I'm, at this stage, I am the first to tell you, I have no idea of future applications. I have no idea. But I understand its meaning. I'm like, maybe like a small-scale Cauchy. I recognize, we recognize the importance. I really don't know, I have some clue, but it is in the future, you know, in the future. Maybe in communications, maybe, who knows. But, so, it is conserved in an ideal situation. It is not conserved in real life, but in real life, the great amount of it dissipates very slowly. So how slowly, then you start to compare with energy. Do they dissipate with the same scale, or which one is more robust to dissipation? And the simple fact that you can compare the two, so they are not order of magnitudes totally different, then the simple fact that you can compare the order of magnitude is relevant. So no need to go into, you know, a lot of details. This is the message.
So you also mentioned helicity reflects some kind of role of three-dimensionality in turbulence or in fluid flow. So that reminds me, recently I used the concept of helicity in my study of collision of two droplets, or you can say collision of two bubbles.
Interesting.
Apparently, because before that I handled X-metric problem. Apparently for X-metric problem, helicity remains zero.
Good.
All the time, no matter it's invasive flow or viscous flow, because simply these two vectors are orthogonal to each other. So then I suddenly realized that once I moved to three-dimensional problem, the helicity just jumps out. It's not equal to zero. So I realized that maybe that can help me to find some interest in three-dimensional.
Is absolutely relevant what you said. Of course, I just mentioned, I said few things, but there's a lot to be said. One thing to be said is what you remarked, that helicity is a pseudo-scalar quantity. It can distinguish left from right, and so it can be used the opposite in the opposite sense. If you have a totally symmetric system, then helicity is zero. When is zero? I reverse the statement. When is zero is any meaning to the fact that is zero? Maybe in terms of complexity, maybe in terms of averaging left and right properties of the system for turbulence, for instance. So this is important. And then there are special cases that are emerging nowadays in which, in physics, where you have helicity always zero, exactly zero. And this is, again, a matter of studying. Why? Why is exactly zero? I'm thinking, again, systems. Yesterday I mentioned harmonic functions and the lack of defects or presence of defects. And then I'm thinking again of the same thing. Bose-Einstein condensates, in certain situations, helicity is exactly zero for the property of the physical system. So helicity can be used to identify properties of that system, structural properties. I'm just mentioning words, the word topology. We didn't talk about topology. We don't know really what is the relationship yet between helicity and topology. We will talk a lot about that in 2 days' time. But for the moment, we just mention the fact that is robust as energy and is there always, but in particular, we can recognize it when there are localized systems, localized structures. Then it's easy. It's easy because you can think of a vortex ring that maybe is linking with another vortex ring. And we are going a bit fast here, but let me just speak again on the remark that we did now, the fact that if there is a linkage, we cannot be in a plane, for instance. We have to be three-dimensional. If we push this link to a plane, we're pushing helicity to be zero. So, although we don't know the meaning of helicity in terms of linking yet, as we are now, but we understand that helicity is measuring three-dimensionality, is robust as it is energy. It scales more or less with the same order of magnitude. So if we are keen on energy, we should learn to be keen on helicity. We are saying that, although I'm anticipating the concept, that is measuring something complex, let's say. And then I add topologically complex. And this is even stronger, because it doesn't matter the shape, as long as it's not destroyed. And then I'm happy to join him in saying, of course, under dissipation, it gets destroyed, but it gets destroyed slowly. It survives for some time. So think of a vortex, a ring linked with another one. Of course, they immediately in water, they get dissipated. But the linkage of what we see with bubbles and the linkage of the field lines is a different thing. The linkage of field lines may survive, although I'm playing with mathematical ideas, but I'm seriously thinking the linkage of the field lines may survive even much more longer than what we see with bubbles. In vortices, is like the powder I said before. We don't see vorticity. So in air, we see some dust that identifies a vortex region, and in water, we use bubbles. Tiny, tiny bubbles that are captured by low-pressure field, and this low-pressure field is at the core of this vortex tube, and so it sucks the bubble, the air bubble. As the electrons travel in these quantum vortices in superfluids. To visualize a vortex in a superfluid, they just shoot electrons, and these electrons travel much faster inside this would be empty structure with vorticity only on the boundary, which makes also another interesting problem to solve. That was done by J.J. Thomson himself. He worked on the velocity induced by a vortex that has only vorticity on the boundary and is empty inside. Again, it's funny, because he did it in 1872, and you can imagine nobody cared about that result. And now we're talking about quantum vortices that are exactly like that in superfluid helium. So it becomes useful, what he did. All this to say that helicity is a measure of a presence of three-dimensionality. And for its own sake, for this reason, enough is to say that is important, to identify three-dimensionality, and three-dimensionality that survives in certain region. Through dissipation, you may have bulk of turbulence that is stronger to dissipate in its structure. And so why helicity survives better in certain regions than others as a tracer for three-dimensional structures. And this is important because we just said that three-dimensional structures carry a lot of energy, a lot of information. Yeah, I should stop here.
May I have a question about the W?
Yes?
My understanding to W is the region where the vorticity omega is non-zero. outside that, omega is 0. And do we have a very clear surface of the region?
No. And this is the question that when I defended my PhD, I was very lucky because one of the examiners one was Derek Moore. Moore and Safman worked together for many, many years on vortex dynamics. And I had Safman, the other one. Safman was a tough man. And Safman, so you can imagine the situation. You are examined by these two guys, and it's not an easy thing. Huh? And with all my enthusiasm, I started talking about vortex tubes like this. And Safman asked me, he stopped me almost at the beginning, which is the terrible thing that you can do to a young man, because you just start with enthusiasm and somebody comes with a killing question. And he asked me, this is a nice idea, Renzo, but how do you define the vortex? Where is the vortex? How do you define it? And then for years, I thought that it was a tube with vorticity inside and nothing outside, and I never thought, this is my definition of a vortex. So when you receive such a question, you think, gosh, this must be a very serious question. So I started to think something, and then I came clean. I said, well, I don't know, this is my definition of a vortex. Yes, but this surface, where it ends, and where is the center of the vortex? Oh, the center was even worse as a question. Because for me, so the center, that was an easy way out. I said, well, the tube has a circular cross-section, and that is the center. But you remember the vortex ring case, huh? Do you remember? We just mentioned before. The vortex ring case has no cross-section circular. It's not circular, the cross-section. The cross-section is not circular because otherwise it does not satisfy the steady vortex dynamic solution. Indeed, for the steady plasma physics solution, the Graf-Schaffernov equation gives you a cross-section that is a D shape. It's not circular. So to choose a torus with a circular cross-section is imposing on nature what we want to do, but it's not satisfying nature, because it wouldn't be a solution of the steady equation. So when I say a vortex is of this circular cross-section, but bends and twists in the fluid, oh, no. Who says that the cross-section stays circular during the motion? It's not circular at all. And I can use the tokamak cross-section to say that it wouldn't be so, it would be obvious to think that the cross-section is flattened on the part of concavity. And then if it twists, this flattened part will rotate according to the pitch of the helix. That would probably be a steady-state solution of a twisted vortex in 3D. Now, to say that the cross-section is circular, of course you understand how far I was from reality. I'm fine, I'm okay if the vortex tube is small, as Kelvin did, very small, okay, so I can assume that the departure from perfect circularity are so small that I can neglect them. That's okay. But if the vortex is thick, who says that the cross-section is circular? Unless it's perfectly, infinitely long as a tube, as a cylinder, untouched, unmoved. So I said that, and he looked at me and he said, I wasn't so happy. So I tried to explain the fact that at the center, I located the points where pressure is at the minimum. Okay, a bit better then. And then he insisted, he said, okay, from the low pressure region, how do you go to a point where you say it's still a vortex, and then the vortex disappears? And then I didn't know. I said, well, it's a model, it's a mathematical model. And then some silence. I thought I was doing very badly. And at a certain point, Moore looked at Safman and said, it's a tough one, this one, Philip, isn't it? We don't know. Oh, if they didn't know, I was relieved. So where the vortex ends is an assumption. You distribute the vorticity on the cross-section on a Gaussian profile. And then below a certain amount of vorticity, below a threshold that you fix, you say that is no longer a vortex. So it's like, I'm here moving to a technical point, but somebody in the audience understand very well. It's like boundary layer theory. If you are, you take above a certain, you go below a certain region where vorticity or velocity, let's say, below when the velocity is 1% of the velocity in the bulk of the fluid, then you are really at the level of the boundary, of the solid boundary. And you define a boundary in that sense. So it's boundary layer theory. So you say when it's below a certain amount, then there is no more vorticity. But you are right, vorticity is everywhere. Is everywhere. So it survives everywhere. And the question of identifying topology more easily is always there, but more easily is when you say, okay, suppose you have vorticity highly localized. Let me go back again to the analogy with magnetic fields. Same thing. They sent satellites, and they sent satellites to measure these structures, so to speak. And of course, ions are everywhere. But you threshold the amount of electric and magnetic properties, and you see very well. Now you go on internet, there are plenty of pictures. It's not simulations. These are real pictures from data from satellite analysis. The SOHO satellite or many other trace satellites, etc. You see beautiful structures that are interacting. And these structures, you can say that here is a plasma loop and here is none. Then there are quantities well known, like the Reynolds number. And you can measure the Reynolds number, which is a ratio between inertia and dissipation. And when dissipation is very small compared to inertia, you say this is a region of ideal fluid, as you can say is a region of zero vorticity compared to the vorticity. Same thing. Same for magnetic fields, of course. You introduce a magnetic Reynolds number. When this magnetic Reynolds number is very large, and the Reynolds number in the solar corona, when I'm thinking of solar corona, I'm thinking of magnetic fields embedded almost in an ideal fluid. We're talking Reynolds number of 10 to 9, 10 to 10, 10 to 8. It means that in the equation, you have Euler equation plus the viscous term. You can rewrite this equation. When you rewrite this equation, you have your Euler plus, and this is, say, dissipation, magnetic effect, etc., etc. And this dissipation, let's say, dissipative effects divided by Reynolds number. You see? These are the equations. So you can imagine to take measure. If the Reynolds number is 10 to 8, who is going to care the 6th or 7th decimal point of your digits? Nobody cares. And this is the Reynolds number in the solar corona, 10 to 8, 10 to... So in fluids, I don't know, but it depends, 10 to 3, 10 to 4. So if it is low, then clearly, then you go to the other extreme. You go to the extreme. So it's a very important extreme, the other one. I'm not talking about the other one because we have 1 week. But what about the other one? Honey, very viscous fluid. Very interesting. You know why? There is a reason. There is always a reason. This world is booming. So before we thought of internet as a way to think of topology that is important and conservation laws, etc. But for viscous fluids comes to mind genetics, DNA, polymers. There are enzymes, topological enzymes, topoisomerases, and they knot and link a long chain. And this long chain is not only a polymer, which is also important for polymer physics, but it can be DNA. It can be a DNA, a knotted DNA. And you understand very well from your intuition that if it gets knotted, then is killing, right? Killing factor, because it cannot duplicate. If it gets knotted, it cannot duplicate and form a secondary DNA from the first. The RNA cannot duplicate correctly, so it's a killer for life. So this can be used by viruses. They attack, they disentangle stuff, they entangle stuff, they reproduce themselves, and so on and so forth. This is done by topoisomerases. That's why topology in modern DNA genetics is a very important business right now. So that's another way to see it. But the simple experiment can be done in any lab, any small-scale, poor money lab. You take a cord of 1 meter long, say, and then you knot it, and then you close the ends, right? And then you leave this cord sedimenting in a viscous fluid, okay? And you measure time. You can measure time. It sediments over a meter height, it goes down, and is knotted. And now you tie a different knot type, and then more knots. And then you study the sedimentation of this same cord, a piece of cord, according to the number, the types of knots you knotted, and also the number of knots you made. The more you knot it, and the more compact it becomes. So the so-called wet surface, the surface of the physical core that is wetted by water, becomes less and less so it sediments faster. And you have an energy spectrum, a spectrum of sedimentation according to knot type. Again, topology is discretizing energy. It's another interesting strand of research of modern applications of topological ideas to fluid flows. Very important for a number of reasons. There is one other reason, so I'm going to use your time to anticipate what I'm going to do in the last 2 days, that is also extremely interesting, is remote from our interest maybe, but is the following. Suppose you go back in time and you are an engineer of 150 years ago, and you think of a metal, how to improve the properties of a metal. So you go to a chemist, and the chemist of the time said, well, you do a mixing of iron with some other substance, and the metal gets highly improved. And you understand what I mean by that. You know, you have a combination of chemical elements in a melt, in a big bulk of one metal, of one element, and then you increase mechanical properties, in particular the Young modulus. So mechanical properties greatly improved. But then the strand of modern research is, well, I don't want to get spurious quantities in the bulk of the metal. I want to increase the mechanical properties just by having an entanglement of the structure of the same molecule. For example, of the same crystalline structure. So these are recent works in that direction. For example, with magnetic fields, I can entangle the magnetic field so that I can structure my system, and that can be used to trap information or to release or to convey information. Again, all this has to do with three-dimensional aspects. And then I stop just mentioning the big and big problem. And the big and big problem is neurobiology. Neurobiology, you know, you give a drug to a tissue, especially on Alzheimer, etc. And the drug helps the nervous connections to restructure. So you have benefit. And why people are not happy? Why the drug is not enough? The drug is not enough because what you get is a rather ordered system. You lack of three-dimensionality. And you don't know how to induce a homogeneous disorder, so to speak. You understand what I mean by that? Because I don't mean really disorder. Otherwise, our brain wouldn't work properly either. But I mean a way where I would feel all the space, or the space full of oxygen and ingredients, etc., would help me to survive in a way like a tree, so to optimize energy, but also to communicate rapidly to very different parts of the same system. And for doing that, you need to understand how to increase three-dimensionality and uniformly distribute the disorder, so to speak. So the first step, the crude step, is at least to get a uniform disorder in 3 dimensions. And then the next step will be, once you achieve that, how to organize the disorder so to be efficient in terms of communication.